Okay, so welcome to the part 2 example video. I'm going to be talking about multidimensional motion. Okay, so in this problem, we want to put a satellite into space. So we strap a shuttle to an airplane, and the airplane takes off, and then it releases the shuttle, and then the shuttle goes the rest of the way. So the plane is initially attached to the shuttle, and it travels up to 15 kilometers in altitude, and it reaches a velocity in the x direction or in the forward direction of 700 kilometers per hour. Then the plane releases the shuttle, and the shuttle falls for a certain period of time. Then its thrusters turn on, and it accelerates the shuttle up into space. But the thing is, there's a regulation that says that if a shuttle is going to intersect the altitude of a plane, it has to be at least 1.5 kilometers away. So what we need to find is the amount of time, the minimum amount of time that the shuttle can drop, so when the thrusters turn on, it will accelerate the shuttle to 15 kilometers when the plane is 1.5 kilometers away. Okay, so how are we going to start this? Well, we know that the plane or the shuttle has to be away from the plane at a distance of 1.5 kilometers. So we're going to do a kinematics equation in terms of the x. So x final is equal to x initial plus v initial time, and I'm going to use capital T for this time and then t for the time that the shuttle falls, plus half acceleration times squared. So first let's talk about the velocity. The plane is traveling at 700 kilometers an hour, and then it drops the shuttle. So the shuttle still has that acceleration. Of course, we're assuming that there's no air resistance or anything like that. So the shuttle will also remain at 700 kilometers an hour in the x direction while it falls. Okay, so the plane and the shuttle are going to be going in the same speed, which means that the rocket is not traveling at any speed relative to the plane because they're going the same speed. They're moving along here. So when the thrusters turn on, our V initial is actually going to be 0 because it's not going any faster than the airplane. Okay, so this is going to go to 0. And since the shuttle gets released from the airplane and it has the same velocity, then there's not going to be a difference of x in between them. So this x initial also goes to 0. So what this formula is going to be all about is traveling a distance of 1.5 kilometers with the given acceleration. Of course, the acceleration is a vector, and it's not going in the y direction or the x direction. It's going somewhere in between. It's going 27 degrees from the x-axis. So we're going to use trig to find the x component. So what we're going to be doing is x final is the distance, and it's going to be equal to 1/2. Acceleration is going to be the magnitude of that vector there, the acceleration vector. So times 30 meters per second, except it's going to be the x component. So we have to multiply it by cosine of 27 degrees t squared. And so we're going to solve for t, which is pretty easy because we have everything except for t. So we're just going to move it over. It's going to be 2 times d, and d is 1.5 kilometers over 30 meters per second squared times cosine 27 degrees squared is going to be equal to t, which is going to be equal to approximately 10.6 seconds. And remember, since this is kilometers, it's going to be 1.5 times 10 to the 3 meters. Now that we have time, we need to solve for the greatest amount of distance that the shuttle can travel in the y direction with that acceleration. Now t is going to be the amount of time that the shuttle is going to take to get from the distance that it falls back up to the same altitude, or to 15 kilometers in altitude. So our y final is going to be 0 because we're looking at it from a reference of 15 kilometers. We're setting that altitude y of a to 0, or baseline. So 0, and then y initial is going to be the altitude that the shuttle falls from baseline. So y initial plus velocity initial, big T. The velocity initial is going to be the velocity that it gathers from falling in the y direction. And then we're going to add 1/2 acceleration t squared. And of course, this is in the y direction. So how do we solve for y initial? Well, the amount of distance that the shuttle falls can be solved with this same kinematics equation, right? So let's say y final is equal to the baseline height, which we've set at 0. So, I'm going to write it down, but this is 0 plus velocity initial. There's no initial velocity in the y direction, so it's going to be 0 t, and this is little t. This is the t that we want to solve for, plus 1/2 gravity times squared. Because the only acceleration when the airplane drops the shuttle is gravity, right? The shuttle drops for a certain amount of time, so the only acceleration that's acting on it is gravity. So the distance that the shuttle falls is going to be equal to 1/2 gravity t squared. Now, in order to solve for the velocity that it gathers while it falls, we have that formula v final is equal to v initial plus a times time. But v initial, of course, the shuttle does not start with any initial velocity, so this goes to 0. And the acceleration in the y direction when the shuttle gets dropped is gravity, so v final is going to equal to gt. And now we can plug these two terms in to this formula and solve for t. So the y initial is going to be equal to the y final from this formula, or the y final from when the shuttle is dropping. So it's going to be 1/2 gt squared plus v initial is going to be the v final from when the shuttle drops. So that's equal to gt. And then multiply t, big T, plus 1/2. And since this is the acceleration in the y direction, it's going to be the accelerations from in the thrusters except in the y direction. So it'll be the magnitude times sine of 27 degrees t squared. And now I'm going to do it up here. Let's plug in our values. We have 0 is equal to 1/2 times negative 9.8 meters per second squared, t squared plus negative 9.8 meters per second squared times 10.6 seconds t plus 1/2 times 30 meters per second squared times sine of 27 degrees times 10.6 seconds squared. Okay, so how do we solve for t? Well, if you recognize, we have a t squared plus b times t plus c, so we can use the quadratic formula, and we'll be doing negative b, which is just going to be 9.8 meters per second squared times 10.6 seconds plus minus the square root of 9.8 meters per second squared times 10.6 seconds squared minus 4 times, oof, my arm's getting tired, times 1/2 times negative 9.8 meters per second squared times 1/2 times 30 meters per second squared sine of 27 degrees times 10.6 seconds squared, and all of that over 2 times a. The half goes away, so we're just going to left with 9.8 meters per second squared, which is going to be equal to negative 27 seconds and 5.77 seconds. And of course, time can't be negative, so it's not 27 seconds. T is equal to 5.77 seconds, which means the shuttle needs to fall for 5.77 seconds in order for the thrusters to push the shuttle to an altitude of 15 kilometers at a minimum distance of 1.5 kilometers. In any case, this has been the example video for the multidimensional motion, uniform circular motion, and also relative velocities. I'll see you in the next concept video.